right, hopefully you have found the script by now. I do want to point out RSiena is occasionally updated. I guess like all packages, right? It takes it a while to get to CRAN. Usually there's a newer package available from RForge that requires some compilation. So let's not do that right now. If you just install the CRAN version, it's the latest as of 2 months ago. It will work fine for what we're doing today. But there's a newer version with slightly more effects out there for those who are just want to be on the cutting edge. So there's an RSiena package. There's also an RSiena test package that is put together that has a lot of things that are in development that people are kind of working on but are not ready for release. That's out there and available. That's where the Bayes version of RSiena is for Bayesians out there. Use it kind of with that caveat in mind that there may not be, again, there may be bugs, there will be bugs, but you can also help with debugging if you want to get involved on that end. Okay, so let's load these up. And then we're going to use some data here that comes with, most of the data comes with RSiena. It's a test data set, but there's some interesting data out there that's not part of the RSiena package. All of this comes from Tom Snyder's SIENA website, which is a huge wealth of information. There's some data there. There's a huge list of papers. There's, most important, there's scripts. There's a page of probably 20-something scripts for how to, tutorials on how to do different things that are useful to work through. So check that out in addition to the manual if you really want to get into RSiena. Okay, so we're going to just set up some functions here that will be useful later for goodness of fit. I'm not going to get into what these do, but they help us calculate some things on the network, some summaries of the network, and we'll call on those a little bit later. Okay. Okay, so we're going to use this data set. It's Scottish data on its 50 adolescent girls in high school, and it's got some of their smoking and drinking and playing sports and other kinds of things. Okay, so I'm going to talk a little bit about the kinds of data that go into RSiena. So we know there's a network, right? And we're going to look at a behavior changing over time. In this case, we're going to look at both smoking and alcohol use. Okay, so here is what we want our data on, in this case, alcohol use to look like. Okay, so we've got 50 students. We've got 3 time points. So we're going to have a matrix here that's 50 by 3. Okay, and if we look at that, we're going to see, okay, we've got wave 1, wave 2, wave 3, all 50 students, their alcohol use levels. Now, importantly, so RSiena, kind of just like the network package in Ergams, it doesn't use any kind of IDs to match up people. It just relies on you having things in the right order. Okay, so you've got a network with people in a certain order. Your attributes and anything else you have should be in the same order. Okay, everything just needs to be sorted that way by you. So keep that in mind. Okay, we can look at our distribution of alcohol use. Okay, looks like a fairly normal distribution, but people are increasing a little bit over time. To look at behavior change and to estimate peer influence, there has to be change. Okay, I found this out in the hard way. The hard way looking at inmates smoking in prison. Once inmates go to prison, they either smoke or they don't smoke. Then they don't change. So even if you have great network data on changes in prison inmates' relationships over time, you can't estimate effects of peer influence because they're stable. So you need some change. So we can look at change. Again, you need some change, but you also need some stability. Some stability that you can use to help kind of some people who are stable that can influence others but aren't necessarily influenced by others. If we look at kind of the cross tabulation, we see, okay, a lot of cells on the diagonal here. That's our people who are stable. We see some off the diagonal. That's good. Those are people fluctuating in their alcohol use. That's what we're going to try to explain. Okay. Overall, half the people in this network changed their alcohol use, half stayed the same. I can tell you that's a good amount of change. We can use that for estimation. There's not good understanding of how much you need, if it's too little or too much. Okay. All right, we're going to do the same thing for smoking. It's got the same data structure. There it's its distribution. Most girls aren't smoking, but by the third wave, we see a number about a third have taken up and are smoking regularly. Now we have no missing data here. A SIENA model can accommodate missing data on attributes as well as on the network. So that's a plus. It is a model. It'll impute missing values, provisionally impute them, and then allow them to change kind of based upon the model over time. So it is a model-based imputation, which is kind of nice. That's a reasonable imputation strategy. The other thing that's nice about having these kind of missing and kind of the model is doing the imputation, not you, is that in calculating those target statistics, so what the network and behavior look like after time 1 that you're trying to use to fit the model, these missing values are excluded from that kind of computation. Okay, so you're not trying to fit imputed values. You're only fitting the data that are actually observed. Okay. All right, let's look at change across time on smoking, and let's see, 1/3 have changed their smoking behavior over time, which, okay, we've got some change. All right, so our networks are these things called S501, S502, S503. I think that's probably here in the description. Yeah, in our help file. Okay, so let's look at the network. Okay, that's pretty ugly. Do we have our S501? Is it shown over here? Yeah, okay, it's not. All right, let's look at see what it looks like. Look at its dimensions. It's 50 by 50. Okay, that's what we want, right? 50 by 50 matrix. RSiena requires a matrix, not an edge list. Okay, so we need actual matrices for what we're doing here. So we have 3 of these, S501, 2, and 3. We're going to create a list for the time being, only so we can do a few other things with them, like let's look at, use this list apply function to get the dimensions of every element in our list. So let's get the dimensions of all of these. All right, good, they're all 50 by 50. That's good. And what if they weren't? Right? Why wouldn't they all be 50 by 50? Right? Some people, drop out of the network. Some people don't answer a survey. Okay, some people join a network. Right? With real data, that's going to happen all the time. With the SIENA approach, what we're going to do is make sure that every wave has everybody observed at any point in time. Okay, so each wave is going to be the maximal set of people observed. If someone's not observed in a wave, we could make them missing. Okay, if they were part of the context but just not there for that wave or didn't answer our survey, then we can make them missing. If they're actually not in the context, okay, so a girl who wasn't at this school and just came later on during data collection, we could include that person. We could be a little bit more efficient if we actually tell the SIENA algorithm that this person was not there until this point in time. And we can do that. There's something called a composition change file that we can create and bring in that tells SIENA who is present and kind of able to form ties at each point in time. And it helps to, again, keeps the number of imputations low. and doesn't have missing data where it shouldn't be. Okay, so we can also look at, let's see, the number of ties at each point in time. Okay, so this is telling us the number of ties, but it's also, again, telling us if we have any missings, okay, which is useful to know. This is a sample data set, so it's nice and clean. Okay. Now we can also stack these into an array. Okay, an array is a three-dimensional matrix, so we're just taking these three networks and stacking them on top of each other, which is the way that SIENA is going to want us to, it's going to want to read in the data in a little bit. So we have to turn them into an array at some point. Okay. Now we can also look at change in the network across time. And just like behavior change, we want there to be enough change, but not too much. Okay, so here we see most ties are 0 and they stay 0, right? But we've got 57 stable ties, and then 56 and 59 ties that change from 0 to 1 or from 1 to 0 across these two waves. Okay. Now we can actually turn this into a number, right? A Jacquard index is a number that captures how much stability there is. It's the proportion of stable ties relative to the proportion of ties observed across 2 time points. So what this is telling us is a third of ties that were present at either time point are present at both time points, which is a sufficient stability. For RSiena, it's advised that stability, this Jacquard, be at least 0.2. Okay, you can get away with slightly less stability if you have a big network, because it's really having a high volume of ties that are stable is really what's important. So a high volume of ties can be help with model estimation, even if a high proportion are changing. Okay, we do the same thing for the wave 2 to 3 transition. We see a little bit more stability there. Okay, and then let's look at our networks here. So always a good idea to look at your networks and get some sense of, let's see. Okay, I was creating a layout there. You probably got to this, but just in case, you can give things the same layout, and it makes it easier to look at what's changed across time. So let's see, there is smoking across the 3 waves, and we see here our initial smokers. And then across time, we see the network becoming bifurcated, right? That group of smokers pulling away from the non-smokers with a few more smokers, okay? Kind of concentrated down there in that lower right area. Okay. Now we can plot both smoking and drinking together. That's kind of fun to do. So here's our drinking. Again, we see the same bifurcation. Our drinkers are down here, the same place where our smokers are. Sounds like trouble. Smoking, or let's see, drinking kind of spreads to this, but we see smoking doesn't spread quite to the same extent as does drinking. Now we could also plot these together using little pie charts. Let's see, do I have a link in there? Yeah, there's a link over here for a paper that has some script on how to do that, because that could be fun to do sometimes. All right, let's get to RSiena though. Okay, so we're going to take this thing we created earlier, this array. Oh, I just lost volume. All right, I'll speak up. So we created an array, these 3 networks stacked together, and SIENA requires that every variable, dependent variable, independent variable, be turned into a SIENA-specific kind of object. Okay, and SIENA has this. There's 6 different things 6 different kinds of objects we can have. We can have behaviors or networks. They can be stable or time changing, and they can change endogenously or exogenously. Okay, and depending upon what kind of variable it is, there are certain kinds of effects that you can do. You can predict change in an endogenously changing variable. You can't predict change in an exogenously changing variable, that kind of thing. So we have to tell SIENA exactly what it is. There is a slide at the very end of the PowerPoint deck that talks about the different kinds of variables and how you create the function you use to create the appropriate SIENA thing, SIENA object. All right, so we're creating a dependent variable based upon this friendship network. We're going to call it friends. Now, by default, SIENA knows that it's a network. Okay, it's just kind of assuming that you're going to have a network there, so we don't have to do anything beyond calling it friends. Now, if we look at friends, it's going to tell us it's a one-mode network. We could have two-mode networks, for those of you with two-mode data. 3 observations, 50 actors. All right, sounds perfect. Now, let's see. Our behavior variable, S50A, is alcohol use. That also needs to be a matrix. It looks a lot like a data frame, right? But it has to be an R matrix. So if it weren't, we would turn it into a matrix. And then we're going to turn it into this thing called drinking and smoking, respectively. Now, we're using the same function, SIENA dependent. We're telling it this is a dependent outcome. It's something we want to model the change in over time. And we're letting it know that this one's a behavior. Okay, this is an individual level behavior. Okay. And then I want to bring in some more attributes. Here is family event data. Hopefully you were able to read that in. This is did a girl experience some kind of change in family composition at each time point. Now notice here we only have 2 time points. Okay. With an exogenously changing variable, what we're saying is that what happens at time t is going to predict change from time t to time t minus t plus 1. Okay, so having a family event at time t is going to be used to predict change in the network from t to t plus 1, and change in behavior from t to t plus 1. For our second time point, that's a family event is going to be used to predict time 2 to time 3. Okay, we don't have a third time point because there's no time 3 to time 4 network or behavior whose change we could predict. So we'll have one fewer temporal observation of anything that's exogenous and changing. Okay. All right, we're going to turn this into what's called a varying covariate, a time-varying covariate. And then we're going to put all of these different SIENA objects together into one SIENA data object using this function here. Okay, and if we look at it, we see, all right, it's really this thing called my data drink smoke. We know what the network is here. Gives us some densities. It tells us about the 2 behaviors we have as well, drinking and smoking, and then our other covariate that we included. Okay. Now we could have created a different network, different structure here. A couple of different ways of doing that. There's a tendency to, you want to create your data once and then be done, right? Because data, that's a step, right? Let's just be done and then move on to modeling. With SIENA, you oftentimes will want to work with different, in kind of an incremental stage. So a very good thing to do is if you're modeling network and behavior coevolution, just start with the network. Okay? Just get a good network change model estimated. Kind of set behavior change aside for a while. It's going to be faster. The algorithm's going to be faster if you're just looking at network change, and you're going to go through a bunch of iterations to get a decent fitting model. As you get a better fitting model, it's going to fit faster. Okay, so you want a good fitting model, and then come in and you add in behaviors as you go. Okay. Now, anytime when you create data and you bring together these dependent variables, when you go to model, or to set up the model, SIENA's got to automatically include some effects for you. And some of those you can't get rid of. So if you tell it that I've got a network, and I have smoking, and I have drinking, and maybe I have marijuana use, and maybe I have sexual debut, and maybe I have delinquency, it's going to want to model all those things. And you can't set them to 0 or turn them off. That's just kind of a feature of RSiena. And so if you just want to model the network, just create a data object that's just the network and use that to specify your model. Okay. Now before we go on, make sure you, let's see, well, we're going to do this, use this my data drink smoke. We're not going to use these, but they're there just for fun. So once you set up your data, and again, you may want to create multiple data objects if you do intend to take this kind of incremental step. Create all those. SIENA has a function that will summarize your data for you, this print 01 report. And it's basically how is SIENA treating your data. So I've got this thing. It's going to go to a file, an output file that's specified here. Looks like this is it right here. It's a text file. And it's a nice summary of the data that you told SIENA you have and how it's treating it. So it's telling us we've got, right, 3 observations, 50 actors, 1 network that changes over time, 2 behaviors, 1 stable covariate, and then it offers a bunch of summaries, right? You've got degree distributions here, out degree distribution. If you haven't yet, check that that looks the way it should, right? That you're using ad health data, people can only nominate 10. Those out degrees shouldn't be more than 10, right? Or your in degrees, you know, they're going to be skewed, but having somebody with in degree of 50, most friendship networks, that's a pretty high number. Okay, so you can look at those here. They should match what you get if you look at your data outside of SIENA. Looking at the behavior variables and actor variables is, I think, where this becomes especially important. Okay, so we've got some missing cases. We've got some means. Okay, these means are of each of our behaviors. Keep track of these because these are the means that SIENA uses to center your variables. So if you want to come back and do some predictions, you need these means. Okay, so it uses the overall mean, not the per wave mean. Okay, let's see. Here we've got the mean of our family event as well as what it is in each of our 2 waves. Our similarity values. So that similarity statistic that I was showing you earlier that's used for homophilous selection as well as peer influence, it's also centered along the way. Okay? These are the values that are used to center, to calculate. This is the average similarity across all possible dyads in the network. Okay, that's going to be used later, so keep track of that. Then we've got some nice summaries of our network at each wave, number of ties. Out degree, no drastic differences there. Here is our Jacards. We calculated these earlier. It's nice to see that SIENA agrees. Okay, and then we've got some summaries of the network as well, including change, behavior change, how many people move down in behavior, how many people move up, the distance down and up. Okay, all sorts of good stuff here that's useful. Again, to gain it's a useful place to gain some sense of what your data looks like. Some of this you will likely be reporting when you report your results. Okay. Okay. All right, so that all looks good. Let's go on to specifying a SIENA model. Okay, we're going to use this getEffects function, apply it to our SIENA data object, and create something called myEffects. Oh, what happened? I don't want that. I want 1 line. So let's try this again. What? That's weird. Okay. So we're going to see something like this. This effects object is the effects that are currently included in your model specification. Okay. Now, keep in mind, we haven't specified a model yet. So these are all the default specifications. We have 4 friend effects. So 4 effects in our network. These rate effects that we have to have. Okay, there's 2 now because we have 2 periods of change, this out degree effect that we have to have, and then a reciprocity effect, a mutuality effect. We don't have to have this, but it's usually a good idea, and it's so usually a good idea that it's just included by default when a network is directed. Okay. We also have effects for every other changing dependent variable that we included. So we've got some 4 drinking effects included in our model, rates, and then a linear and quadratic effect. So these are included by default. The only difference is if you have a 0, 1 variable, that distribution is going to be captured just by the linear effect. You don't need that quadratic effect. Or you can't have a curve with only 2 values, so that won't be included. But otherwise, you're going to have all 4 of those. And then for smoking, you also have 4 effects. So already we've done nothing, but we have a 12-parameter model for this data. Okay. Now, if we were just looking at network evolution, we would have just used the data with the network object, and we'd only have those 4 effects. Okay. So we wouldn't be trying to estimate these things. Okay. Now, the way that RSiena works, and this is going to be helpful in figuring out how you go out specifying effects, is that it will take the data that you specify and calculate every effect it can think of, every possible effect it can think of, and create a list of every possible effect, every possible thing you could do. And by possible, I mean most, because you can still do some user kind of, you can specify interactions that go beyond that set of effects, but it calculates a lot. So this effects documentation will tell us many of the effects, most of the effects we can do with this kind of, with this data here. Okay, and so this is a list. It's a data frame that has effects by their name, those short names I showed you earlier, and what kind of effect they are. So we have about 12, I think, rate effects here. 12 different things that we could do. We could look at the effect of in degree, out degree on rate. We could look at the effect of drinking or smoking or family event on rate. Okay, all of these things that can predict changes in the friendship network. Okay, so this is our outcome here. These are effects we can use. Okay, now notice some of these effects. So for instance, reciprocity. There's 3 reciprocities. These differ over here: evaluation, endowment, creation. We can specify an evaluation version, which is saying, let's constrain the effect of reciprocity to be the same for creating ties as for dissolving ties. Or we could split out creating ties and make that separate from keeping ties. So the endowment is keeping ties. Okay, so we can really specify 3 different effects here. In any model, we can only have 2 of those. We can't have all 3 because they would be redundant. Okay, so how many do we have here? Almost 1,000 different effects. Notice when we get to the bottom, we also have some smoking effects. Partway through, we're going to have some drinking effects. Okay. Okay, so we have here all, a large set of possible effects that includes many of the effects that a person would want to include. I wanted to look at, over here somewhere, we should have my effects. I think it's this one. All right. If we look at it in RSiena, or no, RStudio, we actually see that data frame is a little bit bigger than what popped up in the HTML version. And we see kind of the same effects here, but we also see this column called true, okay, and that's, or a column called include. That's, are we including this effect in our model or not? And we also have a few other things here. Are we going to test our effect, which we'll talk about in a little bit, as well as some other things that come in handy from time to time. All right, so what's happening is when you set up a SIENA model, is you're telling SIENA, come to this list of all of the effects, and let's just pick a few from this list. You used to have to do this with a GUI, with a clicking effects, clicking boxes, which was a nightmare, right? Inevitably, you click the wrong box, run your model, wait 2 days, and then find out you've got the wrong effects. So it's awful. So this, which is not necessarily intuitive, is better than the alternative. So keep that in mind. But what we're doing is we're telling SIENA to go to this data frame and find the right effect that corresponds to the effect I want to include. And so we need to specify a few things. We're going to usually tell it, all right, this is the dependent variable I want to use. Okay, this name column is friends or smoking or drinking. We've got a short name here that refers to the effect. That short name is in the manual, the RSiena manual. And we might have an interaction or two here. So some of these effects, so here we have friendship. We have effective drinking on the rate. So we've got an effect called rate x, and we have the independent variable is drinking here. Okay, we're going to use that information to tell SIENA, come down to here and come to this data frame, find this row, and then come over here and flip include from false to true. Okay, that's how we're going to include an effect for a model. And we're going to do that for every effect that we want to include. All right, so that's what this is doing right here. Okay, this is the effects object we're using. We're going to create it, but a little bit different version of what it was before, and different in the sense that we're going to find an effect with short name avsim. All right, it's going to be, let's see, predicting drinking, and it's going to be predicting drinking based upon friendship. Okay, so this is an effect of peer influence. It looks out at all of one's friends and calculates the average similarity between ego and alter on on drinking. Okay, so that's how we include a peer, this peer influence effect. We could have replaced that short name with these other versions, and then there are still other versions out here that these different versions do different things like weight by the number of alters or not. We could look at similarity versus looking at whether or not our friends are above average or not, okay, which is a little bit different version of peer influence, right? So this average alter effect gets at, if my friends are a little bit above average, are they pushing me to be above average too? Which could be pushing me to be, if it's drinking and my friends are a little bit more drinking, drink a little bit more than average, they could push me to be a lot more drinking than average, which might be dissimilar from them, but it's above kind of the norm or the average within the network. Okay, so we have alter effects that can push to the extremes versus similarity effects that pull toward where alters are. Okay, so that's a peer influence effect. Here we're testing, what is it, that isolation leads to drinking. Okay, and we're getting, every time we're let's see, I don't think I added the peer influence. I gabbed about it way too much, but didn't add it. So let's actually add it. And you'll notice when we add something, we get basically a message here telling us it found it and set it to include equals true. If you don't see something like that, it means it didn't find it. And okay, let's test now. Here we're switching. Let me highlight it. Here we're switching to predicting the friendship network. And we're testing whether ego's value on drinking predicts having ties. Okay, so sending ties. So this is our drinkers more gregarious, more social, have more friends. Okay, here is whether drinkers are more popular. And then here is similarity in selection based upon drinking. All right, I'm going to add some controls for reciprocity, transitive triplets. If I were doing this for real, I would want a more complete set, including degree-related effects. So how does incoming ties affect receiving more ties? How does alters number of ties affect receiving more or sending more ties? there's 3 different versions of these kind of interactions between in degree and out degree that we want to include. All right, let's control for whether there's selection based upon this family event variable. Now notice here we're including 3 different effects on the same line. Okay, a little bit more efficient this way. We can do that so long as these things stay the same. All right, so these are ego alter and similarity for this family event variable. This same X effect is a little different from the sim X effect that we used for drinking and smoking. This is calculating whether or not ego and alter are exactly the same on this variable. Okay, which makes sense for a dichotomous variable, makes sense for categorical variables. Okay, so if you're want to look at whether people in the same category, same group, are selecting each other, you want to use this. You would not want for a categorical variable these ego and alter covariates. Right? These are does having a higher value predict sending or receiving more ties, which makes no sense if those values are categorical. Okay, in which case you'd want dummy variables. Okay, so I've done a lot of research looking at racial ethnic homophily. Okay, in which case we could have one variable that's race ethnic category. We could use same X to get at kind of uniform selection based on similarity on that. But these variables would make no sense. Okay, and if we wanted to look at whether different groups had different tendencies to send or receive ties, we might want some version of this. We'd have to turn these into dummy variables. Turn our data into dummy variables and use these effects on the dummy variables to get at that kind of effect. All right, this is a huge model. All right, effective family event on drinking. And then, so I mentioned transitive reciprocated ties. This interaction might be important. And so I think it is, but I'm going to do this thing here. I'm going to estimate a score test to figure out if I should include it in the model. Okay, so here we're going to include it, but we're going to fix it at 0, and we're going to test whether or not it should be included. And by that, what we mean is we're going to test whether or not the model is able to recreate this statistic well or not. So we're going to calculate this statistic in the observed network, and then we're going to calculate it in all of our simulated networks and see if the model without this effect is able to recreate the number of transitive reciprocated triplets. Okay, if the model's not able to recreate those, then it probably should be included. Right? That's something important. If it's able to recreate it already, then we don't need that effect in our model. Okay, so you can think of this as the difference between a full and reduced model. Okay, and we're testing whether or not what we exclude should actually be added to the full model. Now, the reason to do this is really because this model is, well, two reasons. One is it's computationally expensive to run these models. So adding effects in this kind of forward-fitting strategy where we start with a simple model and then add more complicated effects as needed, it helps things to go a little bit faster. It's also sometimes a very complicated model. It's just impossible to find a good fitting model. There's just too many effects. Okay, and it just can't. It can't find good estimates of all of these effects. So by using a forward-fitting strategy, you get a simple model to fix and then incrementally add more complicated effects and use the previous model as estimates and starting values for where you begin looking for parameter estimates in your current value, in a current model. Okay, so it makes for, helps to fit a very complicated model. Okay, so we're going to do this thing called a score test. All right, I don't think I added it. All right, and then now let's look at what our effects object is. All right, it's gotten huge, right? It's 23 effects, 12 effects in the friendship network. Here is our score test for this effect. Notice that it's included, it's fixed. And it's being tested. Everything else is going to be estimated. We don't have any smoking effects, so let's add a few of those. Okay, and you know what? Let's also test the effects of smoking on drinking and drinking on smoking. Right? That's a benefit of having both of these as outcomes in our model, is we can look at their interactive associations. Okay, so notice these two lines here, they're the same. They both look at this effect from. This is the predictor. This is the outcome. Okay, so we've just flipped around which is predicting which here. Okay, so I think that's enough. So let's go ahead and estimate our model. Quick step we need to do beforehand is set up the model. So there's a few things we need to kind of set. First of all, we're going to give it the output file a name. Okay, it's going to write a text file. We can look at it in R, but there's much more detail that's written to the text file that we might want to look at. So let's give it a good name. And if we use the same name as for our descriptives, it will actually append it to that descriptives, which might be useful. For an example, it's useful. If you start running many models across days and specifications, that's going to get unwieldy, and you probably want to change this anytime you make a significant change to what you're doing. Otherwise, everything gets appended to the end of the last one, and you end up with super long files. Okay, we're going to limit the number of friends to 6 outgoing friendships. These here have to do with the estimation algorithm and how we're able to kind of zoom in on estimates a little more efficiently. We set a C just for the lab so that we should all get the same answers. Okay, all right, so those are our options. And then we can estimate our model here. Okay. All right, so here we're already in phase 2. All right, that's great. All right, we've got 3 phases. We're halfway there. We've got 4 different subphases, and it's telling us how far along in each subphase we are. So here's our current estimate for the first 30 effects in our model. And what we get along the way is how much the simulated statistics, given these estimates, how much they deviate from what we actually observed, in this case at time 2 and time 3. And so what we want is these to be around 0 or jumping, sometimes we're a little bit higher, sometimes we're a little bit low, but on average we're right there predicting the same amount. These are the quasi-autocorrelations. So this is, as we're updating these values, how much are the changes in these values correlated across time. Okay, and what we really want is that these become negative, because sometimes with the parameter estimate, we jump up a little bit, and then sometimes we jump down a little bit. And so we correlate those two, we're going to get a negative correlation. We want those to get to 0 because we really don't want, we want these changes to get smaller and smaller and smaller. All right, now we're in phase 3. We're almost done. We're holding this constant, and we're just calculating some standard errors. Okay. All right, so that ran, and let's see. Interesting. Okay. It gave us some output. Usually you have to ask for the output. Okay. Well, so let's ask for the output. So this my results should give us a very brief version of the output. Some estimates, some standard errors for all of our effects. Our score tested effect has a nice NA in here, and it's held at 0. Okay, we'll interpret that in just a little bit. The first thing we want to do is look to see if this converged. Okay, we get a number here that should be less than 0.25. Okay, this is looking at how well across all of the effects in our model the simulated values match the target values, and we want that deviation to be quite small. So this is less than 0.25. That's good. If it were larger, we would rerun the model, and we would take these current estimates here and use those as the starting values in the next model. So if we run it again, we're going to just keep circling in, hopefully on a little bit better values. Okay, here's some script to do that if you wanted to. If this also were higher and it was stubbornly higher, like we ran it again and ran it again and ran it again and it stayed high, it's probably a sign that our model is bad. Okay, that we have some effects that shouldn't be in there or some and are just having a really hard time estimating. Maybe there's not the information needed to estimate them. We can look at our results object and it gives us a convergence t ratio. Okay, so this is actually a t value for how much the simulated statistics deviate from the target statistics on average. Okay, and that should be quite small, right? Because they shouldn't deviate. So if they deviate a lot, and if any, really 0.1 is a good cutoff here. So if anything, any of these t statistics are greater than 0.1, then that effect is one that's not being fitted very well. Okay, so look here, the statistic that we just calculated didn't fit, but just calculated its distribution. We're not fitting it very well at all, right? So this is an early sign that maybe that's important. We're not matching it very well on average. Okay. Oh, there's a little function here if we want some stars. Some people like those. Tom's a statistician. You don't need stars. You want to know what the coefficient standard error. That's important information. So, okay. All right. Now this summary gives us more extended output that is helpful, but also annoyingly long. It gives us the variance-covariance matrix of our estimates, which is hidden in the other view. So that's useful if you want to do things like test strengths of effects and how kind of look at interactions and predicted values and things like that, but otherwise it's not. But it does give us this results of this score test that we want to know. So we wanted to test whether this transitive reciprocated triplets effect should be included. Okay, and it's telling us, okay, we tested it, we held it to 0, tested it. We get a chi-square value for whether or not its count fit, how well we fit its count. So it's a chi-square with 1 degree of freedom, not very significant, or no, highly significant. So that's a suggestion. We should probably include this. Okay, this should improve the fit of our model. All right, this is actually a pretty reasonable test in terms of if we were to go and add this, it really would be significant. And if this thing's not significant, the score test isn't significant, I've rarely found that if I add it, something that's almost significant, if I add it, it still usually doesn't help model fit. So it's a pretty useful indicator. Okay, all right, so we could add it and run the model. All right, so this does two things. So we included it this time, and then we're going to run our model, and we're going to use this previous answer function and say, take this my results thing that we just estimated and bring in, for every effect that's in both models, bring in those final estimates as starting values. Okay, and we'll then rerun our model. Okay. Are there any questions while this is running? Yeah.
SIENA 07, is there like a 01 through 06?
Oh, that is a fun question. Yes, there is. SIENA started off in this as part of this program called StockNet. And in fact, the listserv, the users listserv group is still called StockNet listserv. But that was built on a number of different steps you had to go through processing your data. So setting up the data, you would use SIENA 01 to help set up your data. You would use the SIENA 02 to help look at some of these descriptives. And there was a series of programs. So this just literally mirrors that. It's just that everything else is behind the scenes now. There is still, I have not used this lately, so with that caveat, there is still a SIENA 08 function. So if you're looking at a lot of networks, there are multiple ways to combine multiple ways to analyze multiple networks. One way is to estimate a model for each network separately. Okay, so if you have schools, estimate a model for each school separately, you get some estimates, and then you can do different kinds of meta-analyses to combine those estimates. If you want to do that in SIENA, there's a SIENA 08 function that will calculate kind of a mean effect, a weighted mean, and calculate a standard error for you. You can also do that outside of SIENA anymore pretty easily, but that's useful. It has a couple of other tests in there that's useful. You could also, though, if your networks aren't too big, and you can stack your networks on top of each other and estimate one model. You use one model estimation across all of your networks. And what that does is it constrains all of your effects to have the same parameter estimate across all the different networks or all the different schools, for instance. It allows the rate effects to vary, but it constrains other effects to be the same, which is really nice. It gives you, if you think these contexts are quite similar and the same rules should apply across these different contexts, it gives you a little bit more power than looking at each network, and you're able to estimate a little more sophisticated the model than you could otherwise. But then it's also constraining effects. It's making the assumption that effects are the same, and that's something that you should test. So there's a way to actually test whether or not these different, really these different transitions have the same parameter estimate. So it could be schools, but you could also use it to test whether or not the same, here we're looking at 3 waves. We could test whether transitions from time 1 to 2 were the same strength as transitions from 2 to 3. So is reciprocity have the same effect early on as it does later on? And depending on our network, we might expect there to be differences or not. Okay, so we've estimated a model. Let's see, this transitive reciprocated triplets effect is significant. Nothing else is. It's a small network, and it's likely has too many effects in it, so that's not super surprising. Oops. All right, so we have a model. Let's see, it should have converged. Yeah, it converged, although not quite as well. Okay, our next step is goodness of fit. So for this, I'm creating this, I'm just giving this a new name, my result's a new name, and that's really because I have all this script written, and I don't want to go in every time and change this to a new object name. So I'm just going to call it myres and use that thing every time. Okay, so let's calculate the fit of the in-degree distribution. Okay, we're going to use this SIENA GOF, SIENA goodness of fit function, apply it to my results here, tell it, let's look at the in-degree distribution, and let's see, we're doing some things here to tell it that whether we want to look at the two, we're basically evaluating fit at time 2 and fit at time 3, right? And we could evaluate that jointly, or we could evaluate fit at each wave separately. Okay, so that's what the join is getting at, and we're saying let's just look at it all together. And that's mainly in the interest of time here. For this, we're looking at, do we want the cumulative distribution, or do we want to know, okay. Oh no, what happened here? Oh, is that it? Okay. Still too small. Can I turn that off? And try it again. Ugh. Wait, that was the wrong one. All right, hey, great. Who said that? Did you? Thank you. That would have been a bummer if we couldn't look at these. All right, so our in-degree distribution, the red line is observed. Okay, and degree 0, 1, 2, 3, up to 8 here, and our simulated in degree, and we're actually pretty good here. All right, this is a nice curve to try to fit, so that's part of it. But our model does quite well. We do have a statistical test down here based on the kind of what's called the Mahalanobis distance, which is how well, it's kind of like a standard deviation, but a multivariate version of a standard deviation. So it's looking at this kind of the standard deviation across the range of values here. So you could think of a 0.05 as a cutoff here, and we're not significantly different, so that's good. Now that said, it's really hard to fit with real data these distributions perfectly. So you could have a really, really close fit, but it still be significantly different, and you could look at it and it looks so good. And oftentimes that's okay. So because our distributions, they're not smooth, right? Our model predicts a smooth distribution. Real distributions are not, and that's the reality of data, and that's just, if we try to get a perfect fit, we're going to risk overfitting our model and not being able to generalize from it. So really, this is great if it's not significantly different, but the eye test is actually pretty good here, and we're getting the overall shape pretty well, and this is, I think, good enough for what we're trying to do. Okay. Now there are a bunch of other goodness of fit things that we could do. I'm not going to go through them. Some of them take quite a while because, right, we're calculating the geodesic distance. That takes a while. For all, we're doing this for all. In this case, we simulated 1,000 networks with our final model. We're going to calculate the geodesic distribution for all 1,000 networks. That takes a while. Triad census takes a while. I'm going to plot the goodness of fit for some of our behaviors. That's pretty simple. Here's the distribution of, what was it, smoking, drinking. Here's drinking. Okay, we've got a very good distribution. Now that's not a hard distribution to fit, right? We've got a linear and quadratic term, that will plot that. So it's not surprising that we're so good, but it's reassuring that we are. We could do some more difficult to fit kinds of statistics. So let's see, we are doing both Moran and Geary here. Ooh, maybe I shouldn't have done that. That might take a while. That's all right. So what we're doing here is we're fitting how well is the behavior. These are measures of network autocorrelation. So they're homophily, but they're homophily at different distances. Distance 1, distance 2, distance 3 in the network, which is something that our model's not explicitly modeling. We're modeling at distance 1 what is homophily, not going further. So we should get distance 1 for these. If we get distances greater, that's a sign our model is fitting well. Okay, so if we can fit these kinds of things, let's see, I think this is distance 1. Moran's eye would give it to us at a distance. I'm not going to do that because I really want to get to all 800 lines here. So I'll leave that for you to go through. Okay, I want to just talk about time heterogeneity. This is what I mentioned earlier. We can test whether or not, in this case, effects have the same effect from time 1 to time 2 as from time 2 to time 3. And let's see, our joint significance tests here suggests they are not different. So the null hypothesis here is that they're the same. And we have no evidence against the null, so it suggests these effects are the same. If we looked at individual effects, which we could do up here, we'll probably see that 1 or 2 are significantly different. Here, this one has a p-value of just under 0.1. All right, smoking effect from drinking, that's less than 0.05. So maybe there's time heterogeneity in this one, but it's also 1 out of 30-something tests. We would kind of expect something to be significant, so it may not matter much. But if you do have serious time heterogeneity in your network or your behavior change, that is important to capture. So for instance, students, when they come to a new school, there's a lot of rapid change in friendships, a lot of rapid change in behaviors as they're exposed to new things. So it would be important to try to capture that and maybe use different allow effects to be different early on versus later in high school. Okay. All right, so interpreting effects, I mentioned and I showed an Eager-Alter selection table. This walks through how you can do that, set up, give it your current values of your model and your data, and then display some results. Actually, I'm just going to run this because I think I like the table or the figure it produces. I think that's fun. All right, so this is predicted values based on egos and alters. Which one are we doing here? Drinking. This is drinking. Okay, so as egos, level of drinking differs. As alters, level of drinking differs. Blue is a higher likelihood of observing a friendship. So we see homophily here, right? People are more likely to choose someone similar to themselves, less likely to choose someone dissimilar. Okay, so more intuitive way, I think, to look at that. And a little bit different version here. If you've got finely scaled attributes, this makes more sense than the other way of doing it. We can do the same thing to look at peer influence. And this can be important as well to understand again, when will individuals change? Under what conditions do individuals change? Okay, so this is a slightly different version of what I was showing you earlier. So given alters with a certain level of drinking, and the labels aren't showing here, but it's low up to high, how likely is ego to adopt each level? Okay, so when alters are high in drinking, this is not a very attractive state. This is a more attractive state of the behavior to adopt. Okay, but when egos are down here, or when alters are here, then being low is a more attractive state, though it's not that much different, right, from going up a little bit. Okay. All right, we're not going to go off on a tangent. I want to get to the simulations here, because this is fun, too. I want to simulate basically some of the results I showed you earlier, but get into just a little bit more depth on how we do that. We're going to reduce the data to 2 waves. It just makes it a little bit easier to work with. And we're going to set up a model and then go ahead and fit the model. All right, so we created just 2 waves of data, and we specified a model. We're going to fit that model, and then we're going to take that fitted model, tweak some parameters in it, and look at what happens to our outcomes over time. Okay. And let's see, I forgot by now what effects. All right, so I do have friends, drinking. I'm now treating smoking as exogenous, just to make this run a little bit quicker. So we're going to look at how different manipulations affect the distribution of drinking in our network. Okay, we're going to set the initial values here equal to what we get from our observed model. Okay, and then we're going to create a new effects object here called sim effects high PI, so high peer influence. And we're going to, all right, there we go. We're going to take this average similarity effect, and we're going to fix it at this really high value of 12. Okay, remember it was something like 2.8 or something earlier? Well, we could look here. All right, this average similarity is 5, all right, with this data. Okay, but we're going to boost it up to 12 and see what happens. Okay, so let's do that. Let's boost it up to 12. And if we look at our object, we'll see it's fixed. Let's see, it's the second to last one here, and it's fixed at 12. All right, then we're going to do the same thing. But we're going to make it much lower. Okay, we're going to drop peer influence down to 0.5. Okay, in a different effects object, And then let's run this thing. Okay, let's run it 50 times. We're not going to have any phase 2 iterations because we're not looking for new estimates. All right, we're just going to have phase 3 estimates and only 50 of them. Okay, and we're going to do this once for high peer influence and then again for low peer influence. And that's why simulations are fun, right? We're done. Okay, now we're going to pull out the mean drinking from our simulations and look at that. The code here gets let's see, I don't have it that way, do I? Okay, the code here is going to get tricky to follow, and I apologize for that, but that's just the way. Did I miss something here? Sin. Okay, that's our initial model. So that should be up here. So my results. I think that's this thing. I swear I tested this out. Okay, that's our okay. No, we need this. I think I just changed a name. That's what happened. Okay. All right, that's the mean of our 50th run here. And what we're doing is this gets complicated because we're taking this simulation and we're coming in and going to the 50th run and the first list of behaviors there and pulling out drinking. It's convoluted. You can dive into it, but it's a really complicated results object that has a lot of things in it. Okay, and all right. So what we want to do is compare our simulation to what we observed. So here's our observed mean drinking at each of those 3 waves. Okay. Let's plot how. Okay, so this is our observed drinking and the variation that we get in that drinking. Okay. This is variation we get if we just let the model run and predict drinking. Okay, we don't get exactly that level each time. We get some variation in drinking. When we make peer influence really high, then we see that mean drinking goes down. Okay, I think that's going to be because we don't have quite as many drinkers here at time 1, which we're basing this on. When peer influence is low, then drinking is allowed to go up over time. Okay, so that's how you can start to pull out just these means over time. What we can also do is we can dive in a little bit further. And we can look at for any single simulation run. Yeah?
Can I just ask about that? It's not really intuitive, right? If peer influence goes up and drinking is going down, or can you?
So it depends on what's normative. And so if the norm is to not drink, then peer influence should pull people away from drinking. If the norm is to drink, then peer influence should pull people towards drinking. So it really depends on the initial conditions and really the distribution, who's popular, who's not popular, kind of in conjunction with that norm. So in this network and this kind of these initial conditions, peer influence actually is a little bit protective. That's not, again, from the simulations earlier, that's not always the case, right? And if we did this in a high school where half the kids are drinking, peer influence is going to send that up through the roof. Okay. All right, so here is mean drinking over time for just one run of the simulation, okay? And here we start here, and these are micro steps. Right? These are micro steps. And as we go along, the network's changing. No one's changing their behavior, but every once in a while, people are changing their behavior going going up or down. Okay, actually, no, this is just changes in behavior, ignoring network changes. If we also come in and bring in some network changes, we get a lot more plateaus here. Many of these flat areas, these are micro steps where nothing is happening with drinking, either because the person who got the opportunity to change their drinking doesn't change, okay? Or these are periods where it's the network that's changing and no one's gotten the opportunity to change their behavior. So overall, this model, we had just over 500 microsteps, right? We can actually, let's see, yeah. These are behavior change microsteps, so we had just over probably about 70 behavior change microsteps. The rest are all network change microsteps. Okay. We can plot these side by side. All right. So I think this might be the last step. So just another way to look at this stuff. Okay, so these are 50 different chains and how individual drinking prevalence changed over time for 50 chains with the same model, same starting values, same model, but just different people picked to change, different people changing in different ways. We can make this a little more intuitive, I think, by using a Loess curve. So there's a Loess curve fit to one chain. And here's Loess curves for all 50 change. So this gives you a different sense of, based on one model, one set of starting conditions, all the different trajectories that, or 50 different trajectories that, or 20, 25, whatever, multiple different ways that, we might see change over time. For the most part, they all increase in drinking, right? We're seeing that, but sometimes it's a rapid increase early on. Sometimes it's no change until later. So we really get a sense of just the stochasticity in the output and the consequences of a model here. Okay. I think that's actually it, and I'm not too far over. All right. So I think I'm going to stop there. If people have questions later, I'll be around for a while. All right. I'm going to stop.
Questions or comments?
Yeah.
I wonder, is there a way to compare results from a standard agent-based model to the SIENA method in terms of predicting outcomes similar, just based on population statistics as opposed to networks?
Yeah, I think totally. You could take any of these, whatever it is you want to predict and summarize from your network, pull it out, and bring in, whatever other approach you have. That would, because as nice and flexible as the SIENA model is, there are things it just doesn't do, right? You're basically, for simulation purposes, you're constrained to whatever effects are in the model, and you're constrained to this one at a time behavior change or network change. It's tough to, you can work with the model to kind of introduce some exogenous shocks, but the endogenous processes are really limited to those two, network and behavior changes. So it's tough to, I think there would be some strengths in comparing it to other approaches that do what SIENA doesn't do. Yeah. All right. Other questions? Yeah.
So it seems like SIENA's kind of like Irvine, that to make a good model, you have to have really good theoretical reasons for the parameters and understand the network. And to me, it seems a lot easier to understand that in a 1 node network than a 2 node. And I was curious if you have any suggestions of how to conceptualize these parameters when applying it in a 2 node network.
Right. So, first I'd say, read the limited literature there is out there on two-mode networks. Read it, because there are, both these and ergoms work with two-mode networks, and there are a small number of papers that start to get at what these statistics are. I mean, some statistics don't make sense. You don't have transitive closure, but you do have 4 cycles. And so you can think of closure in the form of 4 cycles. I mean, I think that a couple of the effects that make sense is 4 cycles are really instances of if I choose these two things, do other people who choose one of those also choose those two? So basically, are these two things chosen together? That's a pretty standard one. You could also, if you know something about the modes, you can control for which kind of, the second mode. Okay, so my work is adolescents and adolescent extracurricular activities. Some activities are just more popular than others. And if you know something about the activities, for instance, things like sports tend to draw more participants than arts activities. So you can control for something about that second mode that might draw more ties. So you can get in degree, out degree, degree effects for the second mode that would be similar to degree effects on, some kids have more friends than others. Some activities draw more than others. And so, attributes, I think the two-mode approach becomes really, you fit the data much better if you know something about those second attributes and can predict which ones are likely to draw. You can actually also do some interactions between, egos of a certain type might be more drawn to, activities of a certain type. Okay, with kids, it's, you have to control for boys play boys sports, girls play girls sports. So you have to control for that interaction of attributes across the two modes. But there may be others. People with certain kinds of other kinds of attributes may prefer whether it's attitudes and what groups you join or something. But I think those would be important to control for as well. Mm-hmm. Mm-hmm. All right, you all. All right, you all are easy.